Hi there, everybody. Today we're going to talk about waves, and there's a lot on this topic in the Wunsch book. There's 2 whole chapters about waves. First, today we're just going to work on talking about waves from the perspective of the general topic. What are they? Where do they come from? Why are they there? That kind of thing. What are the different kinds? We're going to get into the specifics of different kinds of waves, starting with gravity waves, these, in the next 2 classes, and then we're going to start to look at larger scale waves, like the things that have to do with El Nino. There's the famous Slushy Wave from up here. So this is a wave in sea ice. It's actually local. This is a photo from New England that is not actually frozen in place. It's moving, but there's just slushy stuff on top of the water. So the questions that we will begin with are, what is a wave, after all? And we'll revisit inertial oscillations, think about those from the perspective of waves, and then we'll get to this key concept for the kinds of waves we're going to be thinking about. Waves that disperse, that is different wavelengths that separate out over time, and waves that do not disperse, where all wavelengths travel at the same speed. And that's going to give us 2 important concepts to focus on: the group and phase velocities. And then the last piece we're going to talk about is how rotation affects waves. So what is a wave? So often when we're talking about waves like at the beach, we think of the crests, the high part. A wave is not just a crest. A wave has a structure which might be crests and troughs together. It might be something that doesn't really have a recognizable crest and trough. It could be a cyclonic vortex followed by an anticyclonic vortex. And so we'll need to broaden our understanding of what a wave is in order to capture all these different pieces. Waves are also not sinusoidal. Sometimes we use the simplification of a sinusoidal wave to think about how waves work. But there are also packets of waves that might have a limited number of crests and troughs. So unlike a sinusoid, they don't go off to infinity. There's also something called a soliton, which is just a single structure that propagates. Doesn't have really even a wavelength associated with it. And group velocity and phase speed will be closely related to our use of this sinusoidal, how the sinusoidal piece relates to the propagation of other kinds of wave-like structures. So waves at the beach are one kind of wave, surface gravity waves. And we'll get to those. We'll talk about their group velocity and phase speed, what they're like in deep water and shallow water, fun topics like rogue waves and tsunamis. We'll get to that in the next upcoming classes. So oceanographers like to describe waves by where they are and what causes them. So surface gravity waves are at the surface of the ocean, and gravity is the restoring force. So surface gravity waves involve surface waves that are restored by gravity. Okay, let's jump back to what is a wave. So Witham has this famous book on waves, where he defines it as a recognizable signal that's transferred from one part of the medium to another with a recognizable velocity of propagation. That's pretty broad, but it certainly covers sound waves and water waves and that kind of thing. But waves can occur in lots of different types of media, taking lots of different forms. Kundu has a little bit of a simpler definition, which is waves are the means by which information is transmitted between 2 points in space and time without the movement of the medium across the 2 points. I would say without the movement of the medium across the 2 points necessarily. But he's trying to get at the distinction between a wave, which sends information without moving the medium underneath, and a current, which moves the medium from point A to point B. A great example of a wave that I heard from a neuroscientist is if you pour water into a toilet, it'll flush. So he had this idea that he wanted to get a ring of toilets and have one of them, when you flushed it, what went down the toilet would drop into the next toilet, and then he could send a wave around this ring of toilets by causing them to flush in sequence. Really doesn't have to be a sinusoid. So surface water waves, one example of waves. the processes that lead up to El Nino, especially Rossby and Kelvin waves we're going to discuss. Sound waves. Phone calls are an interesting example because they're both a sound wave and a radio wave if it's a cell phone, or a just an electrical wave if it's a landline. Radio is another example. Epilepsy is actually a wave, a brain wave, and a kind of rotating pattern in your firing of your neurons in your brain. Traffic jams are wave-like in terms of the equations that they behave. The northern lights are another wave-like feature. So this is a great quotation from Einstein. The wireless telegraph is not difficult to understand. The ordinary telegraph is like a very long cat. You pull the tail in New York and it meows in Los Angeles. The wireless is the same except without the cat. Anyway, all right. We talked about this rotating tank experiment so many times, we're starting to get bored by it maybe. But what happens as we get towards the end of the simulation is we see these inertial oscillations. Right there, you can see it pretty clearly. Is that a wave? Well, yeah, sort of it is. It doesn't necessarily have a propagating characteristic, but it has this time-dependent characteristic. It turns out that there's something called an inertia gravity wave, which is a blend of the inertial oscillations and a gravity wave that does propagate, and it also senses the rotation of the Earth. Here are the equations for inertial oscillations, which we've already covered before, that we have the Coriolis force, and then we have the time tendency. Notice that the U is here, and then the V is here and here. So these two equations are coupled, which means you can't solve one without the other. But you put them together, you eliminate the V, say, and then you get a second order time differential equation for U, and then you solve it, and you get these two coupled. But it doesn't quite propagate, so this doesn't have, there's no X or Y in here. In fact, it's an ordinary differential equation in time. So are these waves? Yeah, not by the definition that Witham had or the definition that Kundu had, which was propagation of information from point A to point B. So they are time varying, they're sinusoidal in time, but they don't propagate. Okay, but there's some things that we should get used to, which I've been using without defining, so let's get back to that. A crest is the peak of the wave above the still water level. A trough is the bottom of the wave, the part below the still water level. The wave height is typically the distance between the still water level and either the peak or the trough. And the wave length is the distance from a crest to crest or a trough to trough. The orbital path or orbital velocity is the motion that the water makes as the wave passes by, which is often represented as a circle. It is very circular in most cases. And the frequency is if you sit still at a point, it's the number of wave crests that pass point A each second. So bing, waves going by, bing, bing, bing. And then the period is the time required for wave crest at point A to reach point B. Period is how long it takes for the wave to propagate a wavelength. Let's look at a little video that makes this a little simpler. So here we can see that this little bead, which is marking our location of observation, goes from crest to crest. That was the period. Or if we take the length of time and count the number of crests that propagate by, we would have the frequency. Sometimes there's an angular frequency rather than a real frequency like that, which would be 2 pi times the frequency. That's useful because, 2 pi's in the cosines and sines are useful to make that simpler. This is just a different, more mathematical way of writing this. Here's the wavelength, here's the time, and then the time a little bit later. It's propagating. The wave speed is the speed at which a crest is propagating. This is a little bit imprecise for us. What we're talking about here was the speed at which the crest is propagating. So crest to trough to crest is called the phase of the wave. The crest phase, the trough phase, and then back to the crest again at a phase of 2 pi increments if you were using sines and cosines. The phase speed is the speed at which the crests or troughs propagate. The speed at which a particular phase goes. If you track that phase as it moves along, that's the phase speed. The number of wave crests that pass a point at a given time is the frequency, and the period is the time between the crests. Okay, so let's get into an equation that's a little bit more sophisticated than the inertial oscillation, which is the most basic wave equation, the linear non-dispersive wave, which has a constant c here. For some wave property eta, it might be sea surface height, might be something else, could be temperature, could be vorticity, doesn't really matter. We're looking at this equation, and so there's the time rate of change of this property is balanced by the spatial gradient in this property. This is just a 1D version of this to keep things simple, so it's propagating in x, and it's got this constant c. Well, actually, this equation is solved for a constant c by this equation down here, which may surprise you because it isn't a sine and cosine. In fact, it doesn't even tell you what function it is. It's any old function you like of x minus c times t solves this equation. How do we get that? Well, d eta dt gives us the derivative of eta and then the derivative of what's inside with respect to t. So minus c times eta derivative x minus ct. Remember, that's the chain rule. And then this part, plus c d eta by dx eta, is just the derivative of this with respect to x. And it'll have an eta prime, so a derivative of eta with respect to its argument in both terms. Those two cancel because one had the minus c, one had the plus c, and off you go. So it doesn't even matter what function we use, as long as that function is once differentiable, it will satisfy this equation. The second basic wave equation is the linear non-dispersive symmetrical waves. You might have noticed that as x grows and as t grows, x grows towards positive x. This actually only propagates in one direction, toward positive x with growing time, if c is a positive constant. Or you could make c a negative and you would have it propagating only leftward, but you don't have both rightward and leftward waves in the same equation. Just one in this first order equation. In the second order equation, where we now have second derivative with respect to time, second derivative with respect to x, you get a very similar kind of solution, except now you can have rightward propagating part and a leftward propagating part. They don't have to have the same eta, the same function, but you have part of the solution propagating one, part of the solution propagating the other direction. Let's look at what this looks like. So here we have two funny waves. They're triangles, crests, but those are the result of a big triangle at the beginning. And see, this is solving the non-dispersive wave equation, the symmetrical wave equation. And in this case, where we just put a blob of extra water at the middle, or extra property, extra eta in the middle, and it has periodic boundary conditions. Part of it goes one way, part of it goes the other way. Symmetrical. In time, this wave crest, this wave feature is not changing. It is not dispersing. It just stays the same. Sorry, that weird distortion is because it's a periodic boundary, so it's kind of reflecting on itself. Okay, so we said that not all waves are Fourier modes, or sines and cosines, but in fact, we can express any old eta we like. We have those arbitrary functions of eta. We could express them in terms of sines and cosines. And that makes our life a lot easier when we think about dispersive waves, as we'll see. So here is an example of how to do this. You do the Fourier transform of the wave packet. So an eta is constructed by a whole mess of different, that should be dk right there. This is integrated in the wave number over all wave numbers. It's a whole mess of different amplitude functions, which are given at each wave number, times a sinusoidal. Remember, e to the ik x minus omega t. So here, omega, or omega divided by k is equal to c. So we can pull the k outside and then we would have x minus ct like we just saw. Or we could keep it as kx minus omega t. This thing is, this is cosine plus I sine times the argument of the argument. And so this involves cosines and sines. If this is complex, you can pick any arbitrary phase. Here we have a real operator out here, which is sorting out the real part of the signal, which if this was just a real constant, it would be cosine, but since this can be real and imaginary, this can be cosines and sines all added together, all different wavelengths, whole shebang. Turns out you can express any continuous function like this. So all of those etas that we might be thinking about, we could express as a Fourier transform like this. If we consider a single Fourier frequency, just pull out of this integral just one, then that one would be just a sinusoid. It would look something like this, right? We don't know whether we a sine or a cosine because we don't know whether eta has a real or imaginary part, but whatever, it has one of them. And if we plug this formula into this equation, we actually get just, every time we take the derivative of this, we get a k that drops out. So instead of this full formula, we just get the formula that the frequency squared, the angular frequency squared is equal to the phase speed squared times the wave number squared. This is called the dispersion relation, this relationship. A dispersion relation is a relationship between the frequency and the wave number, which tells you how the wave propagates. And in this simple case, where we have a constant phase speed, it's just that the frequency is equal to this phase speed times k. Everybody's squared, so it could be pluses and minuses, which means we have both rightward propagating and leftward propagating waves in this system. Okay. If you have forgotten all of this, you can go back to this slide and look at the sines versus exponents, how you convert back and forth between them. I hope you remember how to do that. Okay, phase and amplitude. So, the amplitude is this part out front, the eta, which is a function of k, or you could think of it as just for each given k, you get a number here, or a complex number here. The phase of the wave is theta, which is this whole shebang in there, kx minus omega t, or kx times ct, that's this thing. When the phase goes from 0 to 2 pi, you reset. And so this is the phase. So when we talk about the phase speed, it's the speed at which lines of constant phase propagate around the domain. And you can see that that occurs when x is at plus or minus ct in this particular relation. When x grows in time and t grows in time, and it's the minus branch, those two could say fixed together. So this c is the phase speed. It's the speed at which you propagate to maintain your phase in space or time. Only the real part of this wave is measurable when we write it like this with a complex exponential. The other part is just there for convenience. So this has both a complex and a real and an imaginary part, but if you take the real part of this, that's the part of the wave that we're thinking about. Okay. Frequency and period, radian frequency and period, or angular frequency and period. So this thing repeats itself every time omega t goes over 2 pi times an integer. So the period is 2 pi over this angular frequency, and the real frequency is f, which is omega divided by 2 pi. These 2 pi's are in there to keep this, the difference of this phase is not repeating every time the phase goes from 0 to 1, it's repeating every time the phase goes from 0 to 2 pi. So there are lots of 2 pi's drifting around, which gets a little confusing sometimes. You can do the same thing for the k part. Here's the wave number, k times x. Whenever that is 2 pi times an integer, you get a repeat in space, now not in time. And the wavelength is 2 pi over this wave number. K is called the wave number. Like the frequency was the number of crests in a certain amount of time, the wave number is the number of waves in a certain amount of distance. Okay. We've already talked about this. Okay. So we talked about amplitude, we talked about phase, we talked about angular frequency, we talked about the true frequency or real frequency, we talked about the period, with the wave number, talked about wavelength. These are the kind of features that you're going to want to be thinking about as we go through these waves. Most importantly, maybe the dispersion relation is the relationship that we're going to talk about most often. Okay, so dispersive and non-dispersive waves. So if C is some constant and it's equal to plus or minus omega k, or if you like, ck is equal to plus or minus omega, then this function has a phase speed that is independent of k. Because you can pull out the k here, you can pull out the omega over k here, and you get c here. Bingo, that tells you that this thing will propagate. So in such a way that the phase of every wave number, every k, regardless of k, has the same speed, the same phase speed c. So the phase positions of different wavelengths, different wave numbers, different Fourier components will stay together. However, if this relationship is not true, then the different phase speeds, every time you change k, you change the omega in an independent way, c is going to change. C is going to be a function of k. So then the different wave numbers will have different phase speeds and will separate out or disperse. So dispersive waves are those where different wave numbers have different phase speeds. Non-dispersive waves are where they all have the same phase speed. Okay, so here's the non-dispersive wave we talked about before. These triangles are actually composed of a bunch of different Fourier components, but they don't separate out, so we don't really care to think about that necessarily. If, on the other hand, we take a simple, this time it's a square wave rather than a triangle wave, but this is in a dispersive limit, you can see the separate Fourier components are beginning to separate out as this wave propagates. We can't easily tell, or maybe you can, whether the longer wavelengths are going faster and the shorter wavelengths are lagging behind or vice versa, but that's the kind of thing that we would think about in a dispersive wave. How fast is a wave? This is a nice example based on water waves, which have the special property that the phase speed is proportional to the group velocity. So here, this red line is marking one particular phase, one particular crest, that's propagating along with a wave packet. And I can't remember whether they're thinking it's going this way or this way. But the wave train travels at half the speed of any individual wave. So the group velocity is the velocity of the whole group, all these wave packets. The phase speed is the speed of one particular crest. So as the group propagates, it's propagating half as fast as this crest is. So in the time that crest takes to get from here to there, the group has not made it that far. The group has only gone, 8 has gone, 8 has actually disappeared. But this side, which was first 5, then 4, then 3, then 2, then 1, see how much slower the group is propagating? But what that means is that the wave crest is forming at the back of the group, overtaking the group, and then disappearing at the front. So this one doesn't disappear in the time we see, but let's look at 8. Here's 8, and 8 gets to the front, and there is no 8. Here's 7, 7, 7, 7 gets to the front, there is no 7. 6, 6, 6 gets to the front, there is no 6. So the speed in dispersive waves of a group is not the same as the speed of the phase. In fact, they're quite different. So let's look at an example of that. So here's a non-dispersive wave with a very complex initial condition. And you can see that all those different crests and troughs are all hanging together. No sense of propagation of the phase faster or slower than the group. They're just all hanging together. What if we do the same initial condition, but in a dispersive wave? Now we see something quite different. In this case, the long waves are clearly faster than the short waves. The long waves are getting out ahead. And then look, watch the phase. The crests are actually propagating. Oh, do it again. The crests are actually propagating a little faster than the group. So you can see that the crest is actually getting out to the front, disappearing, and then another crest is appearing from the back and making its way through. It's maybe easier to see in the high frequency one where the crests are really disappearing and reappearing quite fast. So this is a dispersive wave. This is actually a shallow water wave. So this is one of the dispersive. This is the dispersive case we just talked about. Okay, so how do we express the group velocity and the phase speed from this propagating Fourier version of our wave? Well, we already said that the phase velocity was just c equals omega over k. If it's constant across k for all different k's, that means if omega is proportional to k, then it's a non-dispersive wave. But now we're imagining that omega and k have different dependencies on k, so it does vary. The phase is different wavelength numbers. Well, we could take the derivative of whatever the function of omega is with respect to k, d omega dk, and that's the group velocity. This one is clearly only equal to this one sometimes. If, in fact, the sometimes is precisely when omega is a function of k in just the right way so that c is a constant. If c is a constant, if we take then we get a non-dispersive wave. If we do have a dispersive wave, then we have d omega dk is the group velocity, and the group velocity is equal to the phase velocity when we have non-dispersive waves. You can see that by just moving the k over here. Then we have k times c equals omega. If we take d omega dk, that's d by dk of k times c, and c is a constant, so just c is equal to d omega dk. Therefore, the non-dispersive waves have the group velocity equal to the phase speed. But we knew that anyway because the group of waves back here was propagating exactly the same as the speed of the crests and troughs. So it's not surprising when you have the sense of what a non-dispersive wave is that the group velocity and the phase speed would be the same. I'm also being careful to say group velocity and phase speed for a reason that we'll get to in a little bit, but it's because this doesn't have to be a velocity in all cases. This could be the phase speed can actually be a non-vector quantity, so it isn't actually a velocity. The group velocity is always a velocity. Okay, here's another description of that wave packet, just showing how you can think of the envelope being the group, and then the higher frequency stuff inside being the phase. And as we said, they don't have to have the same propagation speed. And here we go. It's actually, there is a speed, not a velocity. So we should be a little careful about the phase speed versus the group velocity. And here's why. If the phase is traveling like this, and so the crests are moving this way, imagine looking at how fast the crest is moving in this direction as this wave goes from there to there. This direction of the phase speed is actually faster than the direction in between the crests going this way. Because when this one goes from here to there, this one goes from here to there. But think about it, that's the opposite of a vector. A vector goes fastest in its direction, so the velocity is the fastest in the direction of the velocity propagation direction, and then it's smaller as you go around the clock. The phase speed is not fastest in the direction of the propagation. It's quite a bit faster at some tangential angle. So surfers know all about this. Surfers don't surf in the same direction that the wave is propagating. You surf along the wave and you go much faster. So the surfers are taking advantage of the fact that the phase speed is actually faster when you're cutting along the crests of the wave rather than following in the direction of the wave propagation. And so here we go. Here's some surfers looking at this in Pipeline in Pupukea, Hawaii, on the North Shore, which is a great place. You should definitely go. That's an amazing place. But let's see some of these surfers and see how they're using the fact that, see, they are traveling almost parallel to the wave crest, which makes them go much faster than when they go this wave speed. This phase speed is actually pretty slow, but if you go along the wave in the other direction, kind of along the wave crest, you go quite a bit faster. And you want to stay away from these terrifying rocks that are underneath Pipeline by going really, really fast. Okay. So let's look at this video one more time. Here we're watching the long wave separate out from the short waves. We're watching the phase overtake the group. Starting, we can also see the shape of the group as this kind of envelope shape with the phase inside. This is more detail from Wunsch, where he's talking about a group velocity and how you can think about it as being two neighboring waves and how they separate themselves out. This is a bit more elaborate than what we've been talking about mathematically, but it's the same conceptual framework. This is another way of defining the group velocity by doing a Taylor series of this kind of an amplitude function of k times the phase function, or the propagating part of the wave, the faster propagating part. If you do that, you can do some math and you can show that the amplitude actually propagates with this group velocity. The modulating envelope moves at a velocity this. This is called the traveling plane wave, and superposition of traveling plane waves can be a standing wave. Look at this. So this is where we have a rightward traveling wave of the same amplitude as a leftward traveling wave. So if you add these two together, what happens? It actually becomes a spatial function, cosine kx, that's separate from the time varying part. What does it look like? It looks like this. So we see the crest is becoming a trough, is becoming a crest, is becoming a trough. And this is something that happens all the time in like a kitchen sink or a bathtub. If you oscillate at the right frequency, you'll get these waves that build up in amplitude but don't propagate. And it can be formed from traveling waves that are superimposed on top of each other. We haven't talked too much about the fact that the wave equations we started out with were linear wave equations, which means that superposition is okay, just like we had Ekman plus geostrophic plus inertial. We can have leftward traveling wave plus rightward traveling wave because we have a linear governing PDE for the wave equations that we're talking about so far. Here are some other linear wave equations that you might be thinking about. So here is our 1D propagates only in one direction. Here's the dispersion relation, and sorry, we've now switched to having sigma being the frequency, k being the wave number still, c naught being the phase speed. Here is the dispersion for that one. Here's our good old friend, the two-dimensional one. Here's the dispersion relation for that. Here is a one-dimensional one that is in multi-dimensional space, where now the phase speed is a vector, and then you get this dispersion relation. So it looks like that one, except notice that these are both vectors, they're dotted together. Here is the second order propagating in both directions, and now the dot product has become a square of the magnitudes like this. And then here is a really weird one where we have a Laplacian of the time derivative of this one plus beta, our good old friend beta from the beta plane, the Méridien gradient times phi x. This one turns out to be the equation for a Rossby wave, which is something we're going to talk more about, and it has a very odd property that it only propagates its phase only propagates westward. So this is going to be a whole mess that we'll keep thinking about. There's a phenomena called resonance, which is really important for tides. If the wave is going back and forth in an entire basin and the frequency is just right so that you get something similar to the standing pattern, you can actually just keep adding more and more energy into that wave. Every time it goes around the basin, you give it another kick by the motion of the moon. If it's going around once per lunar day, you're just going to spin it up, or twice per lunar day, you're just going to spin it up and spin it up and spin it up, and it's going to go get bigger and bigger. That's how it works in the Bay of Fundy. That's why the tides are so large there. This effect is basically the reason why places that have big tides have big tides. We talked a little bit about 2D. You can imagine defining the phase and wavelength, etc. in 2 dimensions. Sometimes we use K and L like this. K as one component of the wave number and L as the other component of the wave number, then a vector K that's like that. And so wave number is also a vector because it's K dot X in the equation. So Kx plus Ly is just K the vector dot X the vector minus sigma t. That's the phase function. All right, so here is the last set of movies I want to show. This is a plunger, the middle, where I'm just making a sea surface height anomaly by driving a plunger. And you can see that the wave crests and troughs are propagating in and out from my little plunger. Looks nice. Circular waves propagating out. That probably makes sense to you. What happens if we do the same thing in a channel? Well, we got kind of circular patterns to begin with, but then when they hit the walls, they start spreading out like this, and eventually they become kind of linear as they get far enough away, like this. So you have kind of circular, and then it's feeling the boundaries and kind of reflecting and off the boundaries, and then adding up, superposing itself with kind of waves that are going out from the source and waves that are being reflected off the boundary, and they start becoming linear the farther away you go. This has a lot to do with when your radio dies, when you go into the Big Dig or into the tunnel to the Boston airport. So this is an odd case. Here's the same thing. I'm going to plunger in a channel, but notice it's not symmetric anymore. It's going just this way on this wall and just this way on this wall. Turns out this is something called a Kelvin wave, which is a characteristic feature of channel or waves along a boundary in a rotating coordinate system, a rotating frame of reference. We are going to get more into the details of this and think about how this works. It has to do with kind of a geostrophic-like flow in one direction, and then the other direction it's a gravity wave. So this is like a hybrid between geostrophic flow and gravity waves. And if you put the plunger over near one wall of the channel, you just excite this Kelvin wave on one side of the channel. But it's very asymmetric. It doesn't really propagate this direction, it just propagates this direction. Really weird stuff. Named after Kelvin, Lord Kelvin, the temperature guy. He also did this. Had a lot to say, that Kelvin. What happens if we do the not a plunger, but just a blob drop in a rotating system? Well, as you imagine, the blob wants to spread out as a wave, but it's also being affected by the Coriolis force, so it starts rotating. And so if you do this, what do we know about sea surface highs? They form anticyclones. So part of the sea surface high runs away as a wave, but part of it is preserved as an anticyclone that stays put where the original blob was. How much goes away as a wave, how much stays put in the middle, has to do with how big the blob is and how slowly you build it up. If you build it up fast, you're going to tend to excite more waves and less anticyclone. If you build it up on a really big scale, like the whole gyre, it's going to be mostly the Coriolis force, and the wave-like part will be relatively small. But we talked about how we talked about today, about how does the gyro get set up in the first place. It's like this. If you put a blob of water in, or an anomaly away from its steady state solution to be happy with, it would propagate away like a wave, but then leave behind a residual circulation. So this is the way that we can think about how these systems will spin up. And we could do the same blob drop in the channel, and we see now that we have a blob that stays behind, and we also had Kelvin waves that ran away. And if you look very carefully, you can see that this blob is drifting in one direction, which is because this is not just a rotating, this is a beta plane channel. So this way is north at the top, south at the bottom. This is a Rossby wave in a channel. We're going to come back to this as we talk more about Rossby waves. And the last set of examples, which Anna knows better than anybody, is what happens if you have like a blob drop in a rotating channel where you have one side that's elevated and one side that's depressed. What happens? Well, after a while, you get a smooth out drop instead of a sudden jump. And how is that smoothed out piece? Does it continue propagating? No, it actually stays put there. And it does it because it has a flow into and out of the page that puts a Coriolis force back on this pressure gradient. So when we have initial anomalies, they will develop partly into waves and partly into geostrophic flows. That's a process called geostrophic adjustment. And it has intimately to do with this parameter called the Rossby radius of deformation. Hofmuller diagrams are a great tool to use for our last paper. In fact, just making a Hofmuller diagram of a satellite is a cool thing to do. Write a whole paper about that. Here's an example from Chilton and Slacks in '96, which is a paper we're going to come back to. This is discussed in Wunsch, but you can see, look at the red guy. So this direction is longitude. This direction is time. Or I could have done latitude and time, or I could have done X and time, or Z and time. This is the propagation direction. This is the propagation time. And if we track as time increases, these red blobs are moving farther and farther to the west. Farther and farther to the west, farther and farther to the west, like this. So this is a wave-like propagation of a sea surface high, or sea surface low in this case, because this is a westward propagation of phase lines from an altimeter. At a different latitude, we see a different speed of propagation, but we still see westward propagation. And then at still a different latitude, we see even faster speed. I mean, it's even slower speed of propagation. As time is increasing, it's not going as far to the west. This Hofmuller diagram is the idea that you put space on one direction and time on the other direction. Then you look at the structures that are propagated. All right, that's it that I wanted to say about waves to get us an introduction. Lots of pieces here, lots to look at in the Wunsch book, lots to think about for the next paper. See you on Thursday.